Partition string, we're given a string s, and we need to partition it into unique segments by following the procedure. Start building a segment beginning at index 0, continue extending until we see that the segment has not been seen before. If it's seen, then we keep expanding until we exhaust the list. Once the segment is unique, we mark it as seen, so that next time we will know that that segment was seen, and we begin a new segment from the next index. Repeat until we reach the end of S. So we need to return the segments of I, where I is a segment created for that particular index. Right. So straightforward question. Constraints are decent. So what we can do is we can just simulate exactly the things that is said in the question. We keep expanding. We see that E is not yet seen, so we have a set picked, and that set can be used. Initially it will be empty. That set will so we'll add E as an answer for the first index, and then add that to the set. Move forward, B again, we add that to the answer and to the set. We see that B is already seen, so we keep moving forward. BC, we see that BC is not in the set, we add it to the answer and set. We move forward, we see C, so on and so forth. And the thing that we need to take care of is the last element, because that might be left out if we do the usual loop that we do. Okay, so object set is needed st. Let's have an answer. Let's have a string segment. Initially this is the segment, and we keep expanding, we keep adding the characters to the segment. So this is the usual loop. We see that if the segment is not equal to empty, because it can't be empty, right? Then before that, let's check if the segment is present in the set or not. So let's have a check of if it is not present, then we are going to see if the segment is empty or not, because it will be empty initially and it is not in the set. So we have to make sure that we don't put empty set or empty segment inside our answer. If it is not empty, then we insert it through the set and answer. Else we just make the segment, since we are starting with the next index, we are going to reset the segment to that particular character, s of I. Else we are going to take segment plus equal to s of I, and since we have to make sure the last edge case is correct, because the last character may not be present here, it will not be present here because we have not yet found this condition, hence this is not yet processed for the last particular segment of character. So here we need to check if the segment or if the set is not seeing this segment, then we are going to push this. Since this is the last segment, we don't really care about adding it to the set. and we return the answer. Let's see if this works. It does. Let's submit this. Time complexity will be O of n, where n is the length of the string and O of n is the space as well, or actually more than that, because yeah, O of n is going to be the space for using the set. Moving to the second question, here we are given an array of words for index I in the range 0 to words.length minus 1. Perform the following steps. Remove the element at index I from words array. Compute the length of the longest common prefix among all adjacent pairs. Basically we are given words and we are told that for every index, the thing that we are going to do is remove jump and ask the remaining array of the longest common prefix that exists for that particular array at that particular time. Okay. Next time we remove run, so jump is still there, so it is independent in the sense it's like query without affecting the array for the next query. So we do that for run, we remove run and we ask what's the common prefix. We do that for every other index and we build a vector of integer answer. Okay. So for example, if we have something like this, we are going to remove jump and we see that run and run. We are told that adjacent pairs of strings are checked for the longest common prefix, so not the remaining array, my bad. Right, so for run and run we are going to see 3 is the length of the common prefix, so 3 is the answer. We do that by removing run. We see that now the adjacent pairs are not able to contribute to the answer, so our answer becomes the next possible, or the second highest, if we look at it in that way. Right, it's going to be 0, and same goes for the next, and so on and so forth. So the idea is that we can compute the maximum and the second maximum right from the get-go, and we see that if we remove a particular so if we have a string, these are strings. If I am removing this guy, then apart from the remaining original contribution of max and min, max and second max, this is something that can be contributed. So among these three, right, either this or this or this is going to be my final answer, right? So this is only possible if we are avoiding the extreme strings or extreme words, so that needs to be taken care as a edge case. Next thing is max can also not contribute. For example, this is this is the max contribution that we are getting, but now we are at an index this, which means this needs to be removed, so max is unable to contribute what it was contributing in the original words array. Okay, so here we need to make sure that we are keeping track of which index we are removing, and if that index was contributing as my max or a second max previously, right? So if we are storing the index along with this, suppose the first index of the pair which is contributing, if we are storing that along with the max and second max, then we can use this index and see if we still use this contribution or not, right? Apart from the fact that we are having to do this check of next and previous two strings to see if it's contributing or not, if it's maximizing or not, right? So let's write down the steps. The first thing is by the way, getting the longest common prefix is straightforward, a two-pointer approach, so I'm not going to get into that. So the first step is to get the pre-compute the max and second max along with the respective first index of pair. So the pair contains two indexes, so I am going to store the first index. Okay, we can do it either way. By the way, to calculate the max and second max, I am going to use a priority queue of size, basically having a size limit of 2. Okay. Along with it, I am going to store the index as well. Next thing is iterate the I and compute the next and previous, or previous and next word, right? Common prefix, sorry for the language. I hope this is understandable. And after this, get the contribution, basically get the valid contribution, and that's it. There is no cross there. Okay, so this is going to be what basically the length of the words array, with every character being iterated once, right? But actually twice, because we are iterating this guy, except the extreme words, we are iterating all the other words 2 times, probably O of 2 into n, 2 into n into L, where L is the max word that is possible in words, right? And this guy will be similar, I guess. O of 2 into n for every word, and since we have O of n words to process, so O of n into 2 into it, basically again O of n into it. So it's going to be the time complexity. Space complexity is going to be we are not really using anything except the priority queue. That's going to be constant, basically 2 size of 2, okay. So not really some space, it's probably O of 1. Let's see, let's find out. So we are going to have a priority queue. So I'm going to use a minimum priority queue to get the 2 max, right? So straightforwardly, priority queue is going to store 2 values, so I'll have a vector of 3. This is a min heap, so I'm going to have the remaining lambda function. This is a priority queue. I iterate. Let me enumerate. So for every word, I am pushing this, and basically I need to push the common prefix of these 2, right? So why not go one less, so that we have the next word always available? And why not create a function, let's call it get common prefix, this is going to be a 2-pointer approach. Is going to get the common prefix between words of I and words of I plus 1, comma, I is the index I'm going to go with. Get common prefix, so it's going to return integer, like the length of the common prefix. String word 1, string word 2, and when g is equal to 0, when t is equal to 0, while word 1 is or while j is less than word 1 dot length and k is less than word 2 dot length, if word 1 of j is equal to word 2 of k, we move the pointer j and k together, else we just break and return either of the 2 pointer. Let's return k. This is going to be the length, because it's going to be, see, these are indexes, so it's starting with 0, but mind that we are going to go 1 ahead, yes, so it's going to be the length either way. So what we need to check here is, or we push that in the priority queue, we check if the pq.size is containing more than 2, and that actually more than 2, in that case we pop. Right, now comes the other iteration, so we get the answer. Let me get the priority queue 2 values and along with the index in a different let's say variable. Right, here the priority queue is storing the second max first and the first max or the max at the bottom, right? So first I will get the second max, and that might not be present if I have a word size of just 1, right? So I don't even have a second max in that case. So let's keep in mind, let's get second max, let's initialize it with 0 and its index, second index, let's call it, let's keep it negative 1 or something like that, right? So that doesn't affect our answer. Similarly, let's have first max as well. Let's call this max index. Let's call this max CIS. Great. Here, if the priority queue is having a size of 2, that means I will definitely get a second max. So let's get the second max. pq.top 0. Let's get the index. pq.top 1. Let's pop this. If the priority queue size is 1, now in that case I can definitely be sure of getting the max and the max index. Let's copy this. Let's get the max index and pop this. So this will definitely happen because we are given that we have a size of 1 for sure. So what we can do now is just iterate the last the second step, we iterate the words size. We see that let's have a sub answer because we don't really know what's the contribution. So initially we can have a 0 because it could be a extreme case. We can only have a single element. In that case, second max is not a possibility. So we start with the possible answer, that's 0. We see that if I, that is the index, is not equal to the max index, that is this. If that is the case, and since we are only considering the first of the two in the pair, right, first index of the two in the pair, right, so we have to make sure that I plus 1 is also not equal to max index for it to be able to contribute, right. So in that case, sub answer is going to become maxi, else if I is not equal to the second max and I plus 1 is not equal to the second index. I'm sorry, there should be second index, not second max. In that case, sub answer can also, can have second max as the contribution. Lastly, checking for the extreme case and combining the next word and previous word to get the longest common prefix, okay, because that's a possible contribution. Now that we have removed I should not be extreme case first of all, that is it should be within this limit. I should be greater than 0, I plus 1 should be less than words dot size. That means we have two things to combine. So sub answer will become max of sub answer comma get common prefix using this function that we have already created, words of I minus 1 comma words of I plus 1, and that's it. We have the answer. We push that to our final answer. Push back sub answer and we return that. Alright, let's I think I submitted this. Anyways, let's see. This works. Of course, get common prefix. String word 1, word 2. Hope I'm missing I think that's it. Semicolon. Let's see now. Time complexity wise, okay, something's not right. Memory limit except, that's weird. Priority 3. If it's greater than 2, then we pop. It's equal to 2, we pop. It's equal to 2. I see. I think there is a possibility that if we have a minus 1, in that case I guess second index could be 0, and if I see. So the thing is, I made a mistake here. I should not be equal to second max, and I should not be equal to second max plus 1. Okay, that's the second element in the pair, right? Not I plus 1. Similarly, max index plus 1 and not I plus 1. Also, the fact that we are doing a plus 1 and I could be a 0 and max index could be something that is not present at all, or probably second max could be not present at all, right? And I'm doing a plus 1, so I could be, some second max could affect our answer. So let's make it minus 2 to make sure that there's no possibility of it interfering in the answer. And now let's see if this works. Okay, something is really not right. Made a silly mistake here. I should be less than words dot size. And by the way, we don't really need two pointers. We can just do that with just one pointer there. Let me take reference to make things more optimized. So let's see if now this works. Time complexity will be O of n, where n is the number of words, and yeah, again I guess O of n here as well. For every word we are also doing this, which is also going to be just for 2 words, so overall it's going to be 1. Okay. Moving to the third question. Alright, partition array to minimize XOR. So we are given an array nums and integer k, and we are told that our task is to partition nums into k non-empty subarrays such that each subarray compute to some XOR of all of its elements for that particular partition, and among all those XORs I want the maximum XOR. I want the minimum possible value of the maximum XOR. So this minimum possible value is because we have different partitions, and maximum XOR is because for every partitions that I have, I want the maximum XOR to be the value that I want to minimize. Okay? It could be confusing. Usually these kind of problems leads, or at least points towards binary search. It does in here as well, along with DT approach, but that will lead to a TLE because I don't know, it should have passed, but it is leading to TLE. So the constraints are tight, and here we need to use DP. We can use prefix if we need to, prefix array, since we know that XOR works as a prefix as well, like we have for some, right? So XOR has that property, basically A XOR B XOR C. If I want to remove A from that, I can just XOR that A from it, right? So I can XOR other windows with that particular window to get that range that I want. That is not really required here, because I can just do with DP. Basically, if I have A, B, C, D, E, F, and I have I here, suppose I am using DP, then in that case I am keeping track of the current XOR. This current XOR is basically the maximum XOR value that I get for a particular kind of partition that I go with. Okay. So if I have this as a partition and this is the remaining, in that case I am going to maximize this XOR, this current XOR. So I'll have something like current XOR within my DP, which will start with 0. Okay, right. This will be a state, in my DP, and I will basically want to maximize that among all the partition, right? So for that I need the XOR, right? For that, basically, suppose this is the partition that I'm going with, A and then B, C, D, E, F. In that case, I am going to have, right, so this will be the index. I'm going to call the next index, right, because that's the partition. I want to start with the new XOR, so my current XOR will become 0 for this particular recursive function, and I want to just have case of array, so I want to have a key here which will be 1 reduced because I have already done one partition, and this will be maximized with current XOR, right? So eventually I get the value, and this value will be minimized, right? So I'll have an answer which will start with something like int max, right? And this will be minimized. Number answer comma, right? So this is the case. Let's code this up. Let's have mouse.size. Let me take it outside. Right. And I'm going to call the solve function nums, the index, the current XOR, key. Let me write it like key and current XOR. So I'm going to return or uncall this function. This will be nums, this will be index, this will be key, this will be current XOR. So if the index is greater than equal to n, that means I've exhausted. At this point my k should be 0. Only then I want my recursive function to be able to basically contribute to the answer, right? Minimize the answer. Otherwise I don't want to minimize the answer, right? So I would want to return a value that's going to, I mean actually not maximize, right? So I am going to return something very minimum, like current minimum. Otherwise I will return a 0 because I don't have any XOR in this particular partition. So k is equal to 0. If that is the case, then return 0, else return some minimum value. If k is equal to 0, that means I have failed because I have not been able, I am not able to use the entire array, but I have exhausted the partition already. It should be exactly k partition. That means return int minimum. Let's have an answer here now. So this will be int maximum. So I will basically start with this particular index and keep expanding as long as I can. So at this point I will get every element and to a current XOR. Nums of I. So at this point let me get the sub answer kind of by calling the recursive function, right? Or let me call this the remaining XOR, right? This will be the remaining XOR, or basically the maximum value of the remaining partition XORs, right? So this So the I plus 1 comma 0 comma k minus 1, or actually k minus 1 comma 0, okay, because we are moving to the next index, starting a new partition, so current XOR will become 0, and since one partition is done, we reduce the partition. If the remaining XOR is a value that is greater than equal to 0, right, because it can be an int minimum that I am returning, right? In that case I don't want some answer for the remaining XOR to be effective. So if remaining XOR is greater than equal to 0, in that case answer is equal to minimum of answer comma maximum of current XOR comma remaining XOR. This is important, this is very important, okay. And I guess that's it. We return the answer. Let's see, we are going to minimize this. Okay, this works. Let's have a cache. This will be off. This will be a 2D cache. States will be index and k, and dp.resize. I'm resizing with n plus 1 comma k plus 1 comma negative 1. So negative 1 is the default value. If dp of index and k is not equal to negative 1, in that case let's return that and update this as well. Let's see now if this works. Alright, this does. Let's move to the second or the last question. Maximize spanning tree stability with updates. So basically we're given edges, and edges array contains ui vi, indicating the edge in between an undirected edge. A si represents the strength of this edge, and a must I represents if we are allowed to upgrade the strength or not. If this is a 1, we can't really change anything in this strength, and we have to include this edge. If this is a 0, we can exclude this edge, we can include this edge, and if we are including this edge, we are allowed to multiply the strength by 2, and we can do this for this particular edge only once. So for any edge we are going to do we can do the upgrade only once, and that upgrade will be a multiplication of the strength by 2, doubling the strength. What we need to find it is that we need to be able to connect all the nodes with a single edge, right? So there is no duplicate or parallel edge or a cycle, right? And we should be able to get the maximum, actually the minimum strength among the connected edges is a value that we need to maximize, right? So minimum, maximum, maximum, minimum usually leads to us binary search, and in fact we are going to use binary search here, but since we are going to connect the edges and we need to make sure that the edges are just exactly n-1, so exactly n-1 needs to be used, so it has to be a single component by the end, okay? So we are going to use union find and binary search. I mean, there are other ways, more efficient ways, I guess, that we can use, but I'm going to go with this. This is simpler in terms of coming up with, probably, but not as simple in terms of code because it's going to be long code. So union find is what we need. In union find, what do we want this union find to do? Connect. For that we need parent and rank, and it needs to be able to it should be able to tell me if there is a single component at this point or not, or how many components are there currently. So components is a variable that I'll initialize with the number of nodes, and we keep reducing as we merge, right? So we need functions of find parent, merge, and probably is all connected or something like this. And we are going to do a binary search in the range of, let's see the constraint. So it's going till 1e5, right? The edges, actually the strength is going till 1e5, and we are going to go as high as multiplying 2 with this 1e5. So our end will be probably 2 into 1e5. So start is equal to 0 and end is equal to 2 into 1e5, right? So this is where we are going to do binary search. We are going to select a value, the mid, and that mid is going to be basically the stability of the tree. Is this a tree? Yeah. So of the tree, and this stability is used to validate if we can even achieve the stability. But for that we need to do something about the strength, right? We can't really do a DP kind of stuff, right? We can be greedy, but for that we need to sort the edges. But in what manner? Okay. So firstly we need to see that if must is a 0 or a 1, because if it's a 1 we have to include it, right? If it's a 0, then we can have a sort, and that sort could be in a descending order. Why descending order? Because if it has a larger value and the stability that we have decided is even larger, in that case we can just include it without doing any operation, without using any k, right? So here we are given k, right? And we can only use this upgrade k number of times. It should not be exceeding k, and we can do that only once for a particular edge. Okay. So in that case 1 needs to need not use any k, so we can just pre-compute 1 for the entire array. So all the ones are already taken care of. For the 0 we can have a sort based on descending order of strength, and this will help us to validate if that mid value that we have decided upon is correct or not. If it is correct, then we go towards right, because we need to maximize the answer. Maximum possible stability is what we want. Otherwise we go towards left, right? So let's code this and then understand. Let's code the union function. Union will be basically having parent, rank, components we pass n, basically the number of nodes we are going to deal with. Components will be initialized with this n. Parent will be resize with that particular value. Same goes with rank. So parent will be initialized with 0 to 0, 1 to 1, 2 to 2, right, pointing to itself. So I can use a iota function. Basically this will do that. We can do it with a loop as well. It's basically internally doing that itself. And this is iota. Rank is already resized, so we got. So find parent is basically integer n, while n is not equal to parent n. In that case n is equal to parent of n, right? Basically path compression, and this will bring down the time complexity to, I think, O of alpha n, which is approximately O of 1. This is what we are having as function for file parent. We have merge. This will return false if it's already a single component. Otherwise, it will merge and return true. This will help us because this I can use to check if the merge has happened or not. If they are already of the same component, then I'm not going to minimize my whatever strengths that I'm going to do that. So if P1 is already equal to P2, and return false. Otherwise, if rank of P1 is greater than equal to rank of P2, in that case parent of P2 becomes P1 and rank of P1 increments, and else the same thing happens but for P2, and the components is reduced by 1, right, and we return false. We also have a function probably is all connected, which will just check if the components is equal to 1 or not. If it's equal to 1, then all nodes are connected, right? So here this is not going to take care of extra edges that we might have. That needs to be taken care by the merge function itself, because we are returning a boolean. So based on that we can keep track of if we are using or reusing the edge or not, right? So let's come back here. We need to sort the edges. Why not, since we are going to sort it, why not separate the zeros and ones, because we have to pre-compute the ones anyways beforehand. So let's compute in such a way that 0 comes first, 1 comes later, and among them for 0 all the strength will be descending, and so will be the case for 1, which we don't really care, but since we are doing it together we have to do it for both. So basically sort our edges already. This will be comparator. parameter, that is must style, is equal for both LHS and RHS. In that case, return a descending order of strength, okay? That is LHS of 2 is greater than RHS of 2. Otherwise return LHS of 3 less than RHS of 3, right? Now let's recompute, right? For that recomputation, we are already basically going to use that edge for sure. So for that we need a union function or union data structure that we have already created. And let's create a function. Probably let's call this get minimum after taking must edges. Right, the must edges are taken in. So let's create this function, and this is going to return, this is going to update the root and also return the minimum that we get. Okay, so let's have a min start variable. So let's create this function. By the way, this entire code can also be consolidated in a very small portion, but that will not be very helpful in terms of understanding it. So I'm going to be as detailed as possible. So here I am going to have a variable like let's call this mini, and we are going to initialize it to max. We are going to minimize this. So for all the edges, so since ones and zeros are basically sorted in ascending order, so ones will be at the back. So I'll start from the back. I is equal to edges dot size minus 1. I is greater than equal to 0. I minus minus. I'll get the edge in this variable, and if the edge of 3, right, that is must, becomes a 0, that means if edge of 3 becomes a 0, in that case let break. Okay. And if so here we are going to use this edge, right? So let's merge ui and vi, or that is u and v, basically edge of 0 and 1. So root merge edge of 0 and edge of 1. There could be a scenario where in the must section itself we have ui and vi leading us towards having multiple edges, more edges than we required for a node, right? In that case we can just use this root merge function. If it returns a false, that means this edge is already useless or at least redundant, so we don't really need this. And since this is a must, we have to return -1 right from this, right? It's an invalid case. Otherwise we minimize the strength, which is the second parameter, and return that. Alright, so coming back to the function, here we have min start. So if mini start is already -1, in that case I can return -1 right here. Right, now we start with the binary search, n is equal to 2 into 1 into 5, and let's have our answer. Let's have -1 as our answer, because we are going to maximize it, and if we are not able to maximize it, we return -1. But we have to make sure that, suppose this is the binary search section, by the end of it we are returning the answer, but that answer needs to be, taking this into consideration. This consideration has to be minimum of the two, the answer and the min star, right? So we have to return minimum of answer from a min star. Alright, so now let's do the binary search. So the thing is, we are going to binary search, and we are going to use the edge for a particular decided mid. So we are going to change route, but that route needs to be backtracked and reused with the original state. So what I am going to do is create another different copy, I guess, but for that we need to, I can't just do something like this. I have to do a deep copy. So let's create a constructor. So here the constructor will take root, and I am going to get all the parameters from this. Parent, the rank, I'm sorry, the root rank. Alright, so this is it. We go back. So here I am going to get the middle value. I'm going to be careful so that we don't overflow. So I think we will never overflow, but anyways, so here I'm going to check if it's valid or not. Let's create a function is valid. Okay. So here I'm going to pass the edges, the maximum stability that we have decided, or the stability that we have decided for the tree, k, and the union point. Yeah. So if that is the case, this is valid and answer becomes met. We go to the right, so n is equal to met plus 1, else we go to the left, met minus 1. That's it. So let's create the met is valid function, and then we are done. Is valid is going to have edges, so that's going to be vector of n. Then we have stability that we have decided. So let's call this k, and we have the union structure. Let's call this root. So I'm just basically iterating edge. For every edge I am going to stop when I receive a 1, because I know that we are sorted it based on that. So if edge of 3 is a 1, we break. I get the strength, I get the same from edge of 2, I get u edge of 0, I get v edge of 1, and lastly we are going to check if I can include this or not, right? If I can't include this, then there is no point in moving forward, right? So if I can't exclude this guy, this h, u comma v, in that case let's continue. The next check is if the strength value of the edge currently is already greater than equal to stability, that means we are good. I don't really need to multiply by 2 and reuse the operation or do anything. We are good. So if strength is greater than equal to stability, in that case continue as well. So probably I can just take this and put it here. Okay. So I think I shouldn't do this, to be honest, because I have to reuse it, I have to merge it, so that by the end of this valid function I'm going to check the components of the union as well, right? So if probably this will work, but just to be safe, let's keep it separate. I think this should work, but anyways, so if at this point I know that strength would be less than stability, so I have to check if k is greater than 0 and multiplying by 2 makes it greater than equal to stability. In that case we are good. That means I can reduce the operation, otherwise I cannot do anything, right? I have to return false. At this point I have done all the processing. I have to check if the root or this union function is a single component or not. That means the root, is it a is all connected or not. If it is, we will return true, otherwise we return false. Based on that we move to the right or left, right? So let's submit this and see. Okay, union. So this should be end, not root. Okay, this is okay. So everything is what I made for. That's right. (951). I'm passing the union root to this guy. Okay, not bad. I need to pass key as well, I think, or I don't need a key. I just need a root here is what I'm passing. So let's see now. Minister, not minister. Okay, something is not right. see. So we are doing this correctly, at least. And let's see the is valid function. We're checking for every edge. I don't think this leads to no. Probably in the binary search section things are going wrong. Yeah, so we are going right. So end is not what I need to change, and this is where the mistake was. Alright, I found a mistake. Here I was expecting to return true and I returned false. Let's see now. We're good. Let's submit this. Time complexity. This is kind of O of 1 because of path compression, and this is O of edges, so edges log edges. Okay, and this is kind of O of vertices, so we have nodes, so SV. This is also what is it? This is essentially going through all the edges, so in worst case it will be O of E. Lastly, this is a binary search on the strength, so O of log S, but for every binary search we are doing certain something, and this certain something is the valid function which goes for all the edges again, and the merge function is O of 1, so we don't have to worry about that. So this is also going to be O of E log S, and this is the dominating factor I guess. And yeah, that's the fourth problem. Thanks.